Oh, look at this bad boy. This is beautiful, man. Doesn't this thing look awesome? This looks like it should be part of a NASA control panel somewhere. It's I've got to look up the information on when this was made. I'm guessing somewhere in the 60s, maybe 70s. Anyway, this is the Marconi Instruments modulation meter. It'll measure all kinds of things about AM and FM modulation with a very high degree of precision. And speaking of precision, the problem with this one, according to Rick, the gentleman that sent it to me, is that the internal reference oscillator is intermittent. Now, high precision lab gear usually has a very highly accurate 10 megahertz oscillator. It's like a universal calibration frequency in lab gear. And they'll usually have their own built-in, highly precise oscillator, and that oscillator will be oven controlled. It'll be a crystal oscillator with some kind of a temperature compensation or oven that keeps the crystal in the oscillator circuit at a certain temperature and keeps it precisely at that temperature for stability. These will also generally have an input for an external reference, because some labs will have an external super high precision 10 megahertz source, like an atomic source, like based on what is it, rubidium, I think, rubidium, something like that. Maybe it's rubidium. So you'll have a separate device that is your 10 megahertz reference with multiple outputs, and you can run an output to each of your pieces of lab gear, and they will all have the exact same reference source for extreme precision. So Rick says that the oscillator in this guy is unstable. What he said was, I can touch the power lead and it'll stop, and I can touch the power lead again and it'll start. So I'm not sure exactly what that means. If he means the AC line cord, I doubt it. He's probably talking about the power lead on the oscillator itself, so we're going to have to find that. Now, indeed, I have hooked up the output of the reference output to my scope. Let me reposition the camera. So this is the scope. Presently, I've got it hooked in to the back panel of the Marconi, where the reference output is, and as you can see, we've got no signal. Sorry about the low light here, but this is the back panel, and this is standard frequency in and out 10 megahertz. So we got one jack for both the input and the output of the reference oscillator. So you could switch this jack to receive an external reference, or it'll output the internal reference if you want to use this piece of equipment as your reference, right? This jack is external local oscillator in, which I think is a lower frequency oscillator used for modulation if you're generating carriers. I've got to look at the manual to find out for sure. So anyway, we're getting no signal out of it at all, so perhaps that's indicative of the problem. I think that the next thing I need to do is open it up, and we'll find the reference oscillator and see what's going on there. So let's open this bad boy up. Silly me, I almost forgot to turn the camera on. I pulled the cover off, and I was getting ready to take this metal plate off that covers the rest of the circuitry here, and I remembered I should turn the camera on. So just at a glance, when I took the cover off, this thing's very well built, obviously, being high-end lab equipment. There are 4 cards over here in a backplane, and looking at these, they're all digital. These 3 are all digital, so these are going to be the processor. These are obviously ROMs here, so I bet the processor's on this board. This is probably some kind of digital interfacing, and this would be an analog, I bet, front end that processes all the analog signals here, converts them to digital data, which this then maps into memory space. It's got to be. And this is the processor, RAM and ROM. Got to be. And this is probably additional I/O back here to interface with connectors and buttons and who knows what else, digital I/O. because that's just the way it looks. This is an analog board. It has all kinds of analog electronics on it, but it's on the back plane. So obviously that is D to A converters, A to D converters, and all the associated analog electronics to process the analog signals and convert them into the digital medium. Power supply, obviously, over here. And we have voltage adjustments here. Minus 15, plus 15, and plus 5. So 15 volts is not 12 volts is the power rail. That's interesting. And then, of course, a plus 5 volt source because of all of our digital logic. And on the front panel here, there's a bunch of logic behind the buttons, so that's just going to be 7400 series, probably drivers, line drivers that drive the data lines back to here, and buffers to debounce the push buttons on the input. And all the analog magic happens under here, and this is where we're going to find our reference oscillator. So let me finish taking this cover off. Yep. Oh, that's pretty. Oh, that is so pretty. Okay, let's have a closer look at this work in here. So right away, I'm struck by the quality of the isolation. We have, that's steel. We have steel walls between all the different boards and sections. Each wall has these pass-throughs to couple signals through. Here's a ribbon cable here, and the ribbon cable is broken down to all of these little pass-throughs and then reattached at this end. So they don't even just fold the ribbon cable through a slot, because that slot would create a gap for RF. They actually have these isolation poles that come through the metal so that the signals are passed with no leakage, no RF leakage between the panels at all. That's going to be the reference oscillator. I can tell right away. It's a module wired into a board. It's a separate module. Let me look at the... Yep. 44990-418V, 10 megahertz OCXO. So this is our reference oscillator here. It's got 1, 2, 3, 4, 5 wires going down to a board, and this board has some electronics on it. It has a 7400 chip, a couple of transistors, a few resistors. So these 5 wires are what connected. I wonder what they are. Obviously, one of them is going to be 10 megahertz output. One of them is going to be ground. Probably 2 of them are going to be power. This is a crystal oven, right? So it's going to have a heater in there that's going to heat the space that the crystal and the oscillator occupy. So that heater is going to need some current. And they would not want to feed the oscillator with the same power rail as the heater, because every time the heater turns on, you'd have spikes and dips in the power. And the oscillator needs to be fed with an absolutely clean and regulated DC source. So 2 of these wires are going to be power. I don't know which ones yet. I'll have to get the schematic and figure that out. But there's 5 wires, so that leaves 1. What would that other wire be? Probably a trigger of some type. We're talking about an oscillator that is going to be accurate to within a fraction of a hertz, to within a fraction of 1 cycle. So if the oscillator is that accurate, the computer in here needs a way to start the oscillator on a precise millisecond so that it's in sync with everything else. When you're dealing with that kind of accuracy, you know, the space or the time through a complete cycle. Oh, do it this way. There. The time through a complete cycle is a big frame of time, you know, and you're dealing with an accuracy that's within a fraction of that time. So you need to be able to start that oscillator at a precise point in time. So one of those wires is probably going to be a trigger for the oscillator. So before I can start probing this thing, I got to figure out what it is. So let's go to the computer. We'll find the schematic and service manual and see what we can figure out about how this is supposed to work. I found the service manual for the Marconi meter, the modulation meter. And what I'm looking at here is board, the reference oscillator board, the little circuit board that the reference oscillator is mounted on. It's a very nicely annotated schematic. These are the connectors that come in and out to the board, and they're all labeled. 10 megahertz out to somewhere, out to board AC1. That doesn't make sense. 10 megahertz to AB4. This is board AB4. I don't know. Anyway, these are digital signals. This is a 7400 quad gate. It looks like we're doing a bunch of signal switching from the processor. Standard frequency adjust, or pin 5. That must be the trigger. Remember I was saying that there's going to be a trigger on the fifth wire? That must be the trigger that starts the oscillator. We'll have to find the schematic for the oscillator. Actually, I did find it. So, as I was saying, 2 voltage sources. Here's plus 15 volts. This obviously feeds the oven on pin 4. Plus 5 volts comes through a transistor switch to pin 3. So we have some way of turning that power on and off. That must be power to the oscillator, plus 5 volts. It'll be a steady, more regulated voltage. Remember I said the voltages are going to be separated? Yep, there we go. So 5 volts comes through a transistor switch on pin 3. That's a PNP, which means a signal on its base turns it off. So it's pulled up to 5 volts here, which means it's off by default. If this is grounded, it would turn on. And that goes through this NPN transistor as a switch. So this is our signal from the processor that would turn on the internal oscillator. The signal comes in, turns this transistor on, which grounds this line, which then turns on the PNP transistor, which drives 5 volts into the oscillator and turns it on. So that's our processor signal that turns on the oscillator. And then it goes through these gates where it's controlled for switching other things in the rest of the circuitry of the thing. Okay, pin 1 output, that's our output, our 10 megahertz out. So our 10 megahertz out comes into this side of the gate. Our switching signal grounds this side. They're NAND gates, so that would mean that this would be then turning on and off at 10 megahertz. So this 7400 chip is also acting as a buffer for our oscillator signal coming out. And then we've got 10 megahertz here and here, so these are just acting as drivers to drive the signal down these coaxes, 10 megahertz out. So that's what's going on this board. So if our oscillator, I'll have to check and see if the oscillator is even on, and if it isn't on, we can check this switch and this switch transistor to see if they're getting turned on. Cool. What about the oscillator itself? What's going on inside of there? Well, here's the schematic for the oscillator. Isn't that cool? Right away you can see that there's 2 separate circuits in here. This whole section, the crystal oven, is isolated from this section, the oscillator. They share the ground. So what do we got for the crystal oven here? Okay, look at this. These components attach to heatsink, asterisks. So that would be the oscillator transistor, the oscillator crystal, and Q1 over here is on the same heatsink. I see what's going on. All right, 12 volts is coming in. We got a 741 op amp set up as a comparator. And this resistor is also on the heatsink, so this is a thermal feedback. Okay, I see. All right, so this 741 drives this transistor pair. Okay, that's feedback. Drives this transistor, and this transistor is doing nothing more than eating current and generating heat. So it heats up the heatsink that it's on. This variable resistor is also on that heatsink, or this thermal variable resistor is also on that heatsink. So what's going to happen is this is going to turn on, it's going to drive this transistor is going to heat up, it's going to heat up the heatsink until this resistance value drops enough through the inverting input of the op amp to back off on the op amp's output and back off on the drive to this transistor. So that's how this is regulating heat on a heatsink. It's a little feedback loop with this thermal resistor. And that's going to be kind of an analog signaling. It's not like turning a relay on and off and turning a heater on and off. Older crystal ovens were somewhat mechanical. You had a heater element and some kind of a relay or even a transistor that would turn that heater on or off. So it would either be on or be off. This is going to provide an analog feedback path, so it's going to change the drive to that transistor. So it's not just turning it on and off, it's increasing or decreasing the amount of heat that it's producing. That's going to provide a much smoother thermal curve. This, being analog, is going to keep the temperature stable in a much smoother way because it's not turning the transistor on and off. It's increasing and decreasing the amount of heat that it's producing. That's brilliant. So that's what's producing our set heat level on a heat sink that this diode, which is capacitive, is also mounted on it. The crystal, 10 megahertz crystal, is mounted on the heatsink. And T1, which is our oscillator, wow, ZTX 107, that's interesting, is also mounted on the heatsink. So this crystal oven is keeping the crystal, this diode, and this transistor at a constant temperature, constant warm temperature. That's what's creating our stable oscillator. Neat. And we got 5 volts in for the oscillator. Yep, that's our separate voltage rail for the oscillator. 12 volts for the heater. Here's our 10 megahertz output over here on this buffer. This transistor is a buffer. Basically, it's the signal's coupled from the oscillator, and that way this transistor can accept a varying load without changing the frequency that this oscillator is producing. So that's our output. There's our 5th wire, sync. Remember I said there was probably going to be a way of triggering the oscillator? Well, here you go. Look at this. It goes through a resistor right to the feedback circuit here. So I bet you by grounding this, you'll stop the oscillator, and by floating it, you'll start the oscillator, or some other way. Some way that a voltage on this signal is going to start that oscillator or stop it on a precise moment in time. So that is a pulse here from the processor. We'll start the oscillator precisely on a millisecond. So there we go. That's how our high stability oscillator works. All right, let's go back down to the machine and do some probing and figure out why we're not getting a signal out of it. All right, well, now that we know what is what on this reference oscillator, I have hooked up my frequency counter to the output off the back of the unit, and it's showing 0. The scope I've got hooked up to the output on the reference oscillator and no signal, so our oscillator is definitely not producing a signal. So let's look at voltages. All right, I've got my DVM. There we go. All right, so if you'll remember from the schematic, we did have 2 voltage sources. We got a 12 volt source, well actually probably 15 volts, on the yellow wire. So that's the yellow wire down there. .85 volts. That's what's supplying the heater circuit. So yeah, 14.85, 14.86. The power supply's rail is rated at 15 volts. And the 5 volt power is on orange that powers the oscillator. So let's see. 0.6. Yeah, so the oscillator is getting no power. That's why it's not producing any output. All right, well, that leaves us with a couple of possible problems. We could have, well, obviously, the processor might just not be turning on the oscillator. Maybe it's set for an external reference. If it's set for an external reference, they would disable the internal oscillator, fire a relay that would switch signals from this jack on the back so it would feed in. Anywho, first possible problem is maybe not a problem, maybe just a setting. Maybe the processor is simply set for an external reference and disabled this. The other problem could be that there's something wrong in the logic upstream of here, that the signal is not getting through for another reason, and that's what's not turning the oscillator on. Let's check the first problem first. Let's go look at the front panel. Aha! Looky there. Oh, I'm casting a shadow. Right there. Can you read that? External ref. Or external standard. EXT STD. It's set to be using an external frequency standard. That's why it's not turning on the oscillator. So we have to turn on the oscillator. We have to set it for an internal standard. I'm looking at this sheet here. And second function 04, external frequency standard. 0 equals internal, 1 equals external. So the way that we get into these is we press enter and the number. So enter, 0, 4. Oh, there we go. And the current data value for number 4 is 1, which is external standard. So we need to change that to 0. Store. There, it switched to 0. External standard went away. Now it says 54. And let's go and let's see if our oscillator is turned on now. Well, looky there. The output back here on my frequency counter is showing 9.999996. 9.99996. Okay. That's well, that's megahertz, so that's kilohertz. So 960, 970 hertz where it should be a 0. So my frequency counter, if this is accurate, my frequency counter here is off by about 30 hertz. The oscilloscope's frequency display is showing 9.99989. So its frequency counter is off by 110 hertz, if this is accurate. But we're getting signal. We're getting a standard. Now, Rick said that all he had to do was touch the power lead and the oscillator would stop. So the 5-volt power is on orange. Let me get my meter again. All right, and hold it with this hand. Hopefully you can see that. Orange, we should see 5 volts. 4.85 volts. And the frequency is still there. We're still generating. So I'm touching the power lead over and over again, and it's not faltering. I'm tapping it, and it's not faltering. I'm wiggling the wires, and it's not faltering. Okay, Rick. It seems to be working. He said it's intermittent. I tend to believe him. Well, I'll tell you what I'm going to do, I guess. Oh, I can feel the heat. It's just getting warm to the touch. So that heat sink in there is being warmed up to keep the crystal and the oscillator steady. And I've noticed my frequency counter has stopped shuttering between 6 and 7. Now it's shuttering between 7 and 8. So my frequency counter is warming up. This is warming up. I don't know what the warm-up time is on this guy, but I'm going to let it sit for a while. I guess we'll let it cook. I'll let it sit for a few hours, and I'll come back down and wiggle wires again and touch wires again and see if I can get it to fail. Well, it's been about 6 hours that it's been running. I've come down occasionally, and I've bumped it and wiggled wires and touched the power leads. I can, if you can see that on the scope, I can reduce the output a bit by touching the output. But that's just the load, the capacitive or resistive load of my body on its output. If it was unstable, if anything would make it stop, I think that would make it stop. But it's stable. Yeah. I've wiggled things and tweaked things and I can't make it fail. So Rick said the 10 megahertz reference was intermittent or unstable and not reliable, and it certainly seems so to me. It seems reliable to me. So I don't know, Rick. I think the unit's working fine. Perhaps getting bounced around in shipping cleaned connectors on the edge cards or ground points or whatever, that vibration might have inadvertently fixed the issue. So I guess I'm just going to say that it's okay, and I'm going to use it for a while and see how it holds up. For this video, though, I think we'll do one more thing. We've seen what it looks like on the inside and the top half. To end this video, I think let's go ahead and open up the bottom and see what this thing looks like underneath. Well, this is the underside of the unit. All analog electronics under here again, similar to the top. I thought we'd find some more RF-y stuff down here, like a dummy load resistor. But actually, this is the input cable over here, and it runs back and it goes into the area of the power supply. So somewhere in the power supply area is probably the load. The same kind of construction. You know, everything is nicely shielded, separated off from each other, and most of the wires go through these little pass-throughs. This center board is all digital logic, all 7400 series digital logic, so that's probably handling switching, turning circuitry on and off. Processor sends signals out, turns on gates, and they turn on transistors to, you know, energize circuits and do whatever. Other than that, it's all mostly analog electronics in here. It's all very logically organized. It's like they separated the boards out for specific functions. This is the back plane up here for the digital logic boards on top. Oh, I looked at the processor. It's an 8085, not an 8086, an 8085. So that's interesting. Each of these little coaxes has a spring on it to alleviate tension and keep the cable from being crimped or cut by the metal sides of that slot. That's kind of cool. I don't know if I can give you a detail of that or not. Where are we? Here we go. So a coax comes up, goes through this slot in the metal, and on this side of it there's a spring sticking out that the coax goes through, and that keeps the coax going straight through that slot. So it's absolutely clean. It's beautifully put together, absolutely neat. So anyway, that is the Marconi 2305 modulation meter. Could not duplicate the issue with the reference oscillator. It seems to work absolutely fine. I'm just going to put it back together and use it for a while and see if it'll fail. And look for a follow-up video in a week or two where I'll show it in operation. We'll do some measurements with it. I'll show you how it's supposed to work or what it's designed to do. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.